Hello everyone, I hope you're all doing well. I'm Emerson Abbaskuhi, a senior year undergraduate student at the University of Tehran, and I'm a natural language processing researcher and lover as well. And in this series of videos, I'm going to talk about the transformer architecture, and I'm going to implement it as well in both TensorFlow and Pytorch libraries, as I believe coding the transformer architecture can help you to understand it better, because it happened for me many times that I read this paper, I watched a bunch of videos on YouTube, or I read different blogs on Medium, but after that, after some time, I forgot what was exactly happening in the transformer architecture. I think implementing the code can help us to have a better understanding of this architecture. Furthermore, I believe when you are implementing this transformer architecture, you can understand how this is implemented in Hugging Face, which can help you to create your models better for your research projects or any project that you have in your mind. So I hope this series of videos are going to help you to understand the attention and transformer architecture better. We are going to start with reading this paper which introduces transformer architecture in 2017. And this paper was published by Google Brain and Google research team, and we are going to go through this paper from the start to the end, from abstract to the conclusion. I'm going to mention that the way that I'm reading this paper is not the best way, I know that, but that's how I'm going to do that. You can read your paper in the best way that you need, or the way that you are going to do that, but I'm just going to explain how this is working, and then I'm going to implement each part of this architecture. So let's start by reading the abstract model and see why transformer architecture is very important. The dominant sequence transduction models are based on complex, recurrent, or convolutional neural networks that include an encoder and a decoder. So what they are talking about here is that we know working natural language processing needs to have we know we are going to talk about sentences, and sentences have a sequence of words. So we need a sequence transduction, which can happen by before this paper, all of the things that happening for sequence transduction were based on complex recurrent neural networks or convolutional neural networks. So here we can see that the transformer architecture is something that is going to beat recurrent neural networks. The reason that why they are doing that, we are going to see that in the abstract and in the introduction as well. So let's continue the paper. The best performing models also connect the encoder and decoder through an attention mechanism. We propose a new simple network architecture, the transformer, based solely on attention mechanism. What they're saying here is that those recurrent neural networks that were used in the language models before transformer architecture were using attention mechanism, and they were based on the sequence that recurrent neural network sees. As we know, recurrent neural networks see a sequence or word, it sees a word at a time. So there are some problems here. We know that. One of the problems can be forgetting the words that are at the first of the sentence. We can handle that by attention mechanism somehow, but it would not be that much perfect. In addition to that, seeing each word at a time is slow. So the transformer architecture is going to just use attention mechanism to solve these problems. Experiments on two machine translation tasks show that these models to be superior in quality while being more parallelizable and requiring significantly less time to train. So not only they are better in quality, they're reaching better results than recurrent neural networks, but also they're reaching, they need less time to train. Their model achieves 28.4 Blue score on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles by over 2 Blue scores. On the WMT 2014 English to French translation task, their model establishes a new single model state-of-the-art Blue score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training costs of the best models from the literature. So they're mentioning that their model is reaching state-of-the-art results in WMT translation task, both in English and to German and English to French. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. So they tested on the translation task, and they are going to show that their model generalizes well to other tasks as well. So let's read the introduction. Recurrent neural networks, long short-term memory. Recurrent neural networks in particular have been firmly established as a state-of-the-art approaches in sequence modeling and the transduction problems such as language modeling and machine translation. Numerous efforts have since continued to push the boundaries of recurrent neural networks models and encoder-decoder architecture. Models typically factor computation along the simple positions of the input and output sequences. Aligning the positions to steps in computation time, they generate a sequence of hidden states ht as a function of the previous hidden state ht-1 and the input of the position t. This inherently sequential nature precludes parallelization within training examples, which becomes critical at longer sequence lengths as memory constraints limit batching across examples. Recent work has achieved significant improvements in computation efficiency through factorization tricks and conditional computation, while also improving model performance in case of the latter. The fundamental constraint of the sequential computation, however, remains. So, let me explain you what is happening in this paragraph. We are going to talk about the recurrent neural network, how recurrent neural network works. Consider that we have a sentence, for example, the dog ate the cat. Okay, there are some states of the recurrent neural networks. We're going to show that, but basically recurrent neural network is happening like something like this, okay, which this is the state at time t, and this t-1, and this is a state at the time t. Okay, so as I said, the dog ate the cat. We're going to talk about it here. Is a sequence of words or a sentence. What recurrent neural network is doing is to see each word at a time, which is mentioned in the paper by saying that aligning the positions to steps and computation time. There's a computation here, and then the state will be passed to the next recurrent neural network block, and then the next word is fed to the network, and this happens till the end. And after that, we can get the classification result. For example, it's good sentiments or bad sentiments, it's a positive sentiment or negative sentiment. This is happening in recurrent neural networks. So we can see that there are time problems here, and in addition to that, we have the problem of memory constraints that a lot of efforts have been done in these areas to solve these problems. But what they're doing here in this paper, they're going to solve this by introducing a new model. Attention mechanisms have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing modeling of dependencies without regard to their distance in the input or output sequences. So somehow it is mentioning that we have a problem of forgetting in recurrent neural networks, although there are some other architectures such as LSTMs that they are trying to solve this problem, but the problem is still out there and is not solved completely. But using the attention mechanism, this problem can be solved completely using that attention mechanism, because we are seeing all the words not in a time. We are seeing that all of the words in one time, and we are going to make a connection between words using attention mechanism. In all but a few cases, however, such attention mechanisms are used in conjunction with recurrent neural networks. In this work, we propose a transformer, a model architecture, skewing recurrence and instead relying entirely on the attention mechanism to draw global dependencies between input and output and blah blah blah. So they are introducing the transformer architecture to solve the problem that are mentioned in this section for recurrent neural networks, which are the time problem, the memory constraints, the forgetting problem, and all other problems that are not mentioned here about recurrent neural networks. For example, there is a problem with how they are training. A lot of times, recurrent neural networks are not finding the best result when they are backtracking in their model. So that's one of the other problems in recurrent neural networks. So transformer architecture is going to be a good model for natural language processing tasks. Let's see the background. In the background section of this paper, they are going to talk about the problems more specifically and how the transformer is going to solve them somehow. So the goal of the reducing sequential computation that we mentioned that in the previous parts for recurrent neural networks also forms the foundation of the extended neural GPUs, ByteNet, and conv-S2S, all of which use convolutional neural networks as basic building block, computing hidden representations in parallel for all input and output position. In these models, the number of operations required to relate signals from two arbitrary input or output position grows in distance between positions linearly for conv-S2S and logarithmically for ByteNet. So that means how the computation happens is ON. But in transformer architecture, they're using that in constant number of operations. Although the cost of reduced effective resolution due to the averaging attention-weighted positions and effectively contract with multi-head attention as described in section 3.2. So what are going to talk about here is that the transformer architecture is doing that operations at a constant number of operations, which is better than the recurrent neural networks, and the cost of reduced effective resolution due to the averaging attention weighted positions. They're using multi-head attention to solve that problem as well, which will be described in the future. Self-attention that is used as a base and the basic element of this architecture is talked about in this section. Self-attention, sometimes called intra-attention, is an attention mechanism relating different positions of a single sequence in order to compute representations of the sequence. Self-attention has been used successfully in a variety of tasks, including reading comprehension, abstractive summarization, textual entailment, and learning task-independent sentence representations. Let me explain how self-attention works and what do they mean exactly in here. Self-attention is happening like this. Consider that we have that sentence. The dog, sorry about my handwriting, my PC, ate the cat. We're going to talk about this sentence. Self-attention is going to make a connection between each words of this sentence. It's not going to compare it with other sentences. That would not be self-attention. When we are going to self, we are going to talk about this sentence. We're making attention between a sentence and itself. For example, we are going to say that what is the connection between these two words, or these two words, or the with this cat and cat with this dog. So it would be a two-dimensional matrix, or it's better to say it's a matrix because matrix is two-dimensional, that shows the connection between each words of the sentence and how much they affect on each other, how much effect they have on each other. End-to-end memory networks are based on recurrent attention mechanism instead of sequence aligned recurrence and have been shown to perform well on simple language question answering and language modeling tasks. So they're saying that how this idea is coming. They are talking about end-to-end memory networks, that they do not use the sequence aligned recurrence. So that is one of the most important parts of this paper, because it shows how the transformer architecture idea has come into the minds of the writers. The best of our knowledge, however, the transformer is a first transduction model relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolutions. So they're saying that although end-to-end memory networks rely more on attention mechanism, but they do not do that solely. And the first model that is entirely based on the self-attention, the complete representation of the input and output without using sequence-aligned RNNs or convolutional neural networks is a transformer architecture. So, in the next part, which is a model architecture, we are going to talk about how this model works in general. So, most competitive neural sequence transduction models have an encoder-decoder architecture. Let me explain to you what is encoder-decoder architecture. Consider you are going to translate a sentence from English to French. Okay, this is your sentence in English. It has some words, and you are going to reach it in the the French. So it is in English, and this is in French. How this is happening is that they encode this sentence in a space which we call it latent space, which has some features about the sentence. For example, if our sentence was the dog ate the cat, it remembers the whole thing of the sentence, and then it tries to decode it into the French. How it is doing that is, for example, it says that, okay, I know the sentence, I'm going to go to French. I know how to do that, but first of all, I predict the first word. For example, I don't know how it's French, but consider that the word A is for that the dog, okay? And after that, it uses this prediction and that latent space to predict the next word, which is B, and then C, and then D, and we have the translation in French. This is how encoder-decoder model works. So here, the encoder maps an input sequence of symbol representations. For example, consider x1 to xn to a sequence of continuous representation, which is z1 to zn. Given that the decoder then generates an output sequence y1 to ym of symbols one element at a time. At each step, the model is autoregressive, consuming the previously generated symbol as additional input when generating the next. As I mentioned here, that when predicting the B, it not only is using that latent space, which is called Z in this paper, but also it uses the previous word that was predicted here. The transformer follows this overall architecture using stacked self-attention and point-wise fully connected layers for both encoder and decoder. This is the architecture of the transformer. As I said, they are using the encoder-decoder architecture, but how they are doing that is different from recurrent neural networks, because in recurrent neural networks, the last state here in the transformer architecture, we can see it includes an encoder part and decoder part, and now we are going to talk about each part in here. The first thing that's happening here, we can see that the input embedding, we have something about which is called positional encoding. As we said earlier, in transformer architecture, the whole input text is seen at one time. So we should make something to say that this word is before the other word. For example, when we say the dog ate the cat, we should say that, we should show that the dog appears before the cat word. So positional encoding is a way to do that, which we will talk about that in next parts. But after using positional encoding to say to make the order of to encode the position of each word into the text, then we have multi-head attention, which is a kind of self-attention, but it uses multi-head to have parallelization and more speed, which we'll discuss that in the future. And after that, we have add and normalization, which are for making the outputs in better formats. And then we have a feed-forward neural network. In the decoder part, we are seeing that we have the output embedding. We use positional encoding again. We use mask multi-head attention. We are using masking because that's the goal of language model. Language model is going to predict the mask parts. So we are using mask multi-head attention because we have some masks in the output embedding. Then we are using the add and normalization. Then we are feeding the both result of add and normalization in the decoder and the result of feed-forward neural network to then another multi-head attention to make a new attention, which is going to make a connection between input and output to make the model to predict those masked tokens in the output embedding. And finally, we have feed-forward neural network. Then we have linear and softmax, which predicts each word for our language model. This is the simple. This is the simplest structure, and does not contain anything special. And we can see that, as they said, their model solely depends on the self-attention and attention mechanism. And they're using just linear layers, feed-forward neural network, and softmax for other things. Okay, let's talk about the encoder and decoder stacks. Encoder, the encoder is composed of a stack of n equals to 6 identical layers, which we cannot see exactly in here, but each layer has 2 sub layers. The first is the multi-head attention, which we talked about here, and the second is a simple position-wise fully connected feed-forward neural network. They employ a residual connection, which is in the add in here. This is a residual connection, and around each of the 2 sub layers, followed by a layer normalization. That is, the output of each sublayer is layer normalization of x plus sublayer x, which means that what is happening in add and normalization is that we have this input, which we call it x, and we have sublayer, which means that we have used the result of this multi-head attention and passed it to here. It's the sublayer x plus sublayer x are added, and then we are using the layer normalization, where sublayer x is a function implemented by sublayer itself, which here is multi-head attention. To facilitate the result connections, all sublayers in the model as well as the embedding layer produce output of dimension 512. So we can see that the dimension that is used in here, and in addition to that, we can see that our encoder consists of 6 identical layers. So we have 6 in n here that is mentioned here as well. Is a number of encoders. So we have 6 encoders. Each encoder includes a multi-head attention layer and a feed-forward part. About the decoder is also composed of a stack of n equals 6 identical layers. In addition to the 2 sublayers in each encoder layer, the decoder inserts a 3rd sublayer which performs multi-head attention over the output of the encoder task. So, as we said, we're passing this as well, saying that it performs multi-head attention over the output of the encoder task. Output of encoder task is fitted to this multi-head attention. Similar to the encoder, we employ residual connections around each of the sub layers, followed by a layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. We will talk about this in the future, but it's exactly saying that, as we talked about, we are going to predict the mask tokens. So, to predict the mask tokens, you should not see the future words. It is that sublayer is to prevent that thing happening. And this masking, combined with the fact that the output embedding are offset by 1 position, ensures that the predictions for position I can depend only on output as a position less than I. This is what I explained earlier. It means that, for example, we are going to imagine that the C word here is a masked token. So it's a masked token, and we are going to predict that. It means using that kind of attention for predicting this mask token, we are just going to use A and B here, and we are not going to use D. For position I, we are just going to predict it dependently on the previous tokens or previous words. this is how decoder works. And as we can see, again, we have n equals to 6. So we have 6 encoders and 6 decoders in each transformer layer. New models such as BERT, I don't know, Electra, or any other language models that are using transformers use multiple transformer architecture, and they change the number of heads of this multi-head attention and other hyperparameters, and they have millions or billions of parameters. For example, GPT-3 contains, if I'm not wrong, it contains 175 billion parameters, and that's a huge model. In addition to these things, some of the language models that use transformer architecture just use the encoder part or the decoder part based on their goal and the language model they are training. So that should not be something unbelievable for you, because this is a transformer architecture, but how it is used in other language models, it depends by the idea that they are using. Now let's talk about the attention mechanism that is the most and the core feature of this architecture. An attention function can be described as mapping a query and a set of key value pairs to output, where the query keys, values, and output are all vectors. So it's somehow we are going to find out the connection using this attention by using queries, keys, and values, and all of these things are vectors. And we know that the vectors are word embeddings. The output is computed as a weighted sum of values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. Okay, let's see this. We are not going to talk about multi-head attention here exactly, but we are going to talk about the scale.product attention, which we are going to implement it in this part of our series of videos. What is exactly happening in a scale.product? Let me explain you what are key, query, and values before we dive into the paper. So I'm going to have this. Okay. We said that we are going to have a key, a query, and a value. Basically, how you are going to introduce these things it depends on you and what you are going to use for them. One thing that we can use for this, as we know, each word has a key and a value, and query is the thing that we're going to search through all the sequence of words. And basically, query and key are the same thing, but the query is the vector that we are going to search for it in the series of keys. One thing that we can use for all of these vectors is word embedding. We can say that the key and query are word embedding and value is word embedding. And how we are going to do that. And why we are going to do that. How we are going to do that is not that much simple. We have different word embedding models. We can use them to create embedding for each one. But why we are going to use word embedding for all of these things? Let me explain you. Although the word embeddings are in higher dimensions, but let me say that we have a vector for a word in a 2D dimension, which is in here. And this is, for example, the key that we are checking with. And this is the query. What we're going to do is to say that how much these two words affect on each other. The thing that we're going to use is to say we can map this query vector on the key and say this is how query do itself in this in the way that the K is showing the word, showing the meaning, showing the sentiment. This is how we are going to do that and why we are going to do that. The connection between query and keys can be done using the word embedding, because query and key are going to introduce that how much these two words, how much these query and key are going to affect on each other, how much they are in the same way talking about something. That can be the mapping of Q on key. So because of that, we're going to scale dot product. As you know, to calculate this Q prime here, what we are going to use is to use dot product between Q and K, and then we are going to divide it by the size of K, which is important for us. So let's dive into the paper and how they are going to explain that. As you can see, first we are going to check this query and key. We are going to find that the size of the map of Q on K, which is which we defined it as Q prime here. Here, what we're going to do is basically in this section, what we do is to calculate that the size of query Q prime, the size of this. And then as we are going to say, is it's a vector, then we are going to multiply it by V, which we use the Q as well. I mean, here the Q and V, the K and V are the same thing. They are both the word embedding. And when we are going to matmul these two vectors, it means that we found that Q prime is, the size of Q prime is 2. Then we are going to set 2 of K, 2 of unit vector in the way that the K is directing, which will be this Q prime vector. I hope that I explained it in the way that you need. Okay. What multi-head attention do here is basically it, instead of using just one simple scale product, it uses multiple heads to make it faster, and it uses parallelization for that, which will explain it in the future. We are not going to do that, but in this part. But you should know that multi-head attention is not a new thing. It's just a scaled product attention, but it uses parallelization to make it faster. Okay. Here is a formula for this k.product. How they are doing that is very simple. As I said, they are going to calculate the dot product of the query and key, which is calculated by multiplying these two matrices in this way, which is the dot product, and then they are going to make it a normalized version, which they divided by the square root of dk, which is a dimension here, and then they are going to get a softmax of that, and then they multiply it by v to find out how q and what is the q prime vector here. Okay, now we are going to implement this scale.product here, both in TensorFlow and Pytorch, to understand it better. Let me do it in here. First, I'm going to use Pytorch. So I create a new file which is called, we can call it as scaled .product.python, and we are going to implement it here. So what we're going to need, I'm gonna make it bigger, we're going to need math, and we're going to use Torch. So from Torch we are going to use NN, which is the neural network. Now we are going to implement that scale.product. So I create a class scale.product, and I'm going to inherit from NN module because it's kind of a layer. Okay, as you can see in the picture of multi-head attention, we can see that it uses multiple scale.product attention layers. So because of that, we are going to use a module of neural network, and we are going to see that as a layer. Okay, we have a constructor for that. In this way, we are going to first of all call the super constructor, which is a constructor of this NN.module class, and we are going to pass this scale.product, or better to say scale.product attention, to this class and solve that underscore init. After calling the super, now we need to use that softmax that was introduced in this formula. So we need a softmax. To use a softmax, we are going to use a softmax of Pytorch. So we are going to say softmax is equal to nn.softmax of dimension equal to -1. Then we are going to define the forward, how the forward is happening in this layer. So we have self, we have a query, we have a key, we have a value, and we're going to say use mask or no, and then we have an e, which I will introduce you to that in some seconds in the future. Okay, this is the forward method. And now what is going to happen in here? As we know, we need batch size. As batch size, we have head, we have length, and we have the dimension of our tensor, which is k.size. All of these things are equal to the size of our embeddings. Now, what you're going to do is to calculate the key transpose. As you can see in this formula, we are going to find out the key transpose. For this, we are going to do that using the transpose method of the key vector here. And we are going to pass it 2 and 3 to find out the transpose of the key matrix. Now we are going to find out the score. Score is somehow the thing that's happening in this softmax. So we are going to say that Q multiplied by this transpose vector, and then we are going to find the square root of that dimension dk, the tensor, and we calculate that it is here. We calculated this as a score. Then what we're going to do is to say if we have a mask, we should do something. Okay. But what happens if it's not none? I will explain this in a few seconds later, but let's say that we do not have mask. What you are doing was just going to say calculate this softmax of this score that we calculated, and then we are going to say that the v is score multiplied by v, and then what we're going to do is just to return v and score, which is the size here. This is score and this is v. We're going to return both of those things. But a big but that's happening here is, what if we have mask? to talk about it here, it's not something simple at all, because we do not know how this is exactly happening here. For now, we are just going to say that consider we have a mask filling method, and we are going to use that. For example, we are going to say that score is score.masked fill, which doing that function for us, and we are going to say mask is equal to 0, and we're going to pass this e. So for now, we are not going to talk about these things that much because we are not sure how this is exactly happening. We are not that much familiar with the masking. We will come back to this part in the later in the future videos, but for now we just consider that if we are going to use masking, we're doing it in this way. But how we are going to do that, we will explain it in the future things. So this is the scale.product. It was not that much hard. Now let me first of all commit my change. So added scaled.product in Pytorch. Okay, and I'm going to implement it in TensorFlow as well. So the TensorFlow, as it would be easier, we are going to say that we have a modules, and we are going to define all of those things in here. So we may need NumPy and TensorFlow as TF in here. So let me explain that thing for you here. So def scaled dot product attention, you're going to use QKV and key masks, and we have other parameters here as well. For example, consider we have causality, which is false. We have drop out rate, which is 0 for now. Or we have training, and we have scope, which here is scaled dot product attention. You will see how these parameters will work in this section. Let me do it here. Okay. First of all, we are going to say with tf.variable scope which we are going to pass scope, and reuse equal to tf.auto reuse. We are going to use this variable. It's exactly the same. Decay, or the dimension, was mentioned here. We are going to say that q.get shape dot as least -1. We are going to use the last dimension of this Q matrix. Then we're going to say outputs is equal to tf.matmul q, and the transpose of that K matrix now that we have that thing, we're going to output would be outputs. It's better to say in it this way. We're outputs or it's better, I should say decay. That's the square root of that decay. Now it's better to use port math. Let me do it in this way. Instead of math, that's square root of this dimensions. And then we are going to use masks. So we're going to say mask outputs and key mask is equal to key masks, and the type would be key. How this masking is happening in here, we'll introduce that in the future videos again. So the type here is key. Now we're going to say that if causality is happening, what you're going to do is to use that masking, which is like how we used here in this mask in this way. So what would be the causality here? The causality would be very simple. We're going to say outputs is equal to mask outputs, and the type here would be future. Now we have outputs equal to TensorFlow.neural network.softmax, and I'm going to calculate the softmax of the outputs, and then we are going to say what is the tension. The tension would be the transpose of outputs and after calculating that transport, we're going to say tf.summary.image attention would be tf.expand beams attention until the next one, and the axis would be this. So finally we are going to use a dropout. So outputs tf.layers.drop out. We're going to pass it that output, this rate, dropout rate, that training. And now finally we are going to say that outputs would be the math multiplication, your matrix multiplication of that outputs with the v vector. So that's simply happening. Now after using this thing and calculating these things in here, we are going to return that outputs. So that would be so easy. So this is the implementation of scale.product both in TensorFlow and Pytorch. I'm going to commit this, git add all, git commit -m, added scaled.product in TensorFlow, and then now we have it. So that was it for this video. I will see you in the future videos. We are going to talk about the multi-head attention. We are going to talk about the other things such as position encoding, how that encoder is doing its things, how the decoder is doing its thing, and then we are going to connect them to each other and use it as a transformer architecture. So, to the next video, goodbye.